So last week we saw the economic order quantity. In this model, demand was constant. And therefore we could measure Q star and the cost related to Q star. Okay. Today we will deploy this problem a little bit more, but not in a mathematical way, or not so much in a mathematical way, but more intuitively. And now imagine you have one machine, okay? You know the demand, you know you have to produce every day, or no, not every day, every month. No, every day, yeah, every day. Every day, 300 units of product A, 200 units of product B, and 100 units product C. Okay? Just imagine, right? This is your constant demand. Every day the same. A total of 600 units. Okay? And this machine has a cycle time. We know two parameters, cycle time and changeover time. Okay? The first question that we make is, how does the production plan look like? The daily production plan. First question. Second question that we make is, how much inventory should we carry between machine 1 and machine 2. This is machine 1, and we don't know how much inventory we should carry, if any, between these two machines. And the third question is, how flexible is our process? So today we are going to answer these three questions. Okay? And for it, in order to answer the three questions, we need a lot of knowledge that we still don't have, and we will learn it today. Does it make sense? So we are a production leader, or a maestra, or how you call it. You want to know, you have your cycle time of machine 1, your changeover time of machine 1, you have your cycle time of machine 1 or 2, and your changeover time Machine 2, you have these parameters. And you want to know your daily production plan for machine 1 and 2. How much inventory should we carry between machine 1 and machine 2? And how flexible is our process? So there are a bunch of concepts here that are probably unknown to you. Okay. The first concept, just focus on these questions. Okay, we want to answer these questions. The first is, what is a process? I'm too fast?
Change over time.
Change over time. I explain in a minute what this means. First, we need to know what is a process. Okay? So what is a process? A process is a sequence of actions that change one input into one output. Process step 1, 2, 3, 4, and so on and so forth. A process is a sequence of actions that change one input into one output. Go in, always trying to sell something to a customer that we describe as a heart, because the customer beats. Sometimes the customer wants more, sometimes wants less. Okay? So we move from input to output. What do we move? We move material, we move information, we move money, we move energy, a bunch of things. So we transform one input, raw material, into one output. Does it make sense? Easy, right? So the customer gives us something back for the product. What does he give us back? Money, right? So the customer is paying back with money because this product, this output, is of value for him or for her. We are moving material, information, money, and so on and so forth. So this movement is about a flow. We're talking about value flow, or a better word, stream. So when we talk about a process, we talk about a value stream. We are creating value for a customer through the stream. Okay? This creation of value takes place by taking into consideration these steps. These steps could be these machines. Okay? Between these machines, we will need later on inventory, as we will see in a minute. Okay? Any questions about the definition of a process? Any questions? So when we talk about a process, we talk about a value stream, and these words can be interchanged. So if we ask, how flexible is our value stream? It's the same. Yeah. Can I? Better? Good. Any questions? So a process is a value stream, a value flow, a value stream. And what do we create with this process? We create something of value for our customer. The customer changes its demand with time. In a general case, in this case, no. Okay, in this case, it's constant still. Later on, next week, demand will get changing, and then things will get tough. Remember to study statistics again, okay? Bring your statistics knowledge back to your forebrain. We will need statistics here. So demand is changing with time. And because demand is changing, we need to adjust our supply. Let me take another color. We need to adjust our supply to demand. What happens if somebody here have a boyfriend or a girlfriend and you want to tell? Jemand hat eine Freundin oder einen Freund und möchte das auch sagen? Ja? Wenn du jetzt, if you supply to your girlfriend more supply, okay, than she wants, then you have a problem. Okay, if you want to give more than she wants this day, this moment, nein, du hast ein Problem. Sie will dich nicht sehen, also am besten haust du ab. Wenn du weniger lieferst, if you supply less than she wants, you also have a problem. Makes sense, okay? So you always have a problem, exactly. So the idea is to always supply whatever your girl wants, okay? And then everybody's happy. So in order to have a zero gap between supply and demand, we need to have a very flexible process. So we're going to measure flexibility by the way we can adapt to our customer demand. Okay, we will see in 1 hour how we do that. We measure flexibility by how we can adapt our supply to customer demand. One example is Opel today. They in Rüsselsheim, they have Kurzarbeit. They bring down the amount of people working. Yeah, doesn't matter. You adapt your supply to the demand. You bring less people in to work, so you produce less because demand is going down. So we measure flexibility by how good we can just intuitively, we can adapt to customer demand. Okay. Later on, we will see how we measure it effectively. Why we need inventory between the processes? Any idea? Any idea? Well, the key is here. These two little numbers, the definition of cycle time and change over time. So remember this is important. The whole thing is just qualitative, but we are seeing very important things. Cycle time, per definition, is the time between two same parts produced by one machine. So I end producing one part, until I end producing the next one. Okay, this is the cycle time. Every 10 seconds, every minute, boom, 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 one car every 5 minutes going out of the line. Okay, this is the cycle time of the process. The change over time is the time between two good different parts. Last good part from A, first good part of B. In the meantime, you perform a changeover process, changing the tools, changing stuff, the jigs and rigs into the machine, so that you can produce not car A, you can produce car B, or red to yellow, or whatever. Okay? So last good part from A to first good part from B. These two definitions are important. So far, any questions? Imagine this is a production line of cars, okay? And this is a press. Look at, please look. This is a press mill, and you press the doors, and here you mount them. You mount them at a speed that is 10 times faster than what you press here. Or you press here 10 times faster than what you mount here. Because the press just goes chung, 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 chung. Every 2 seconds you can press one door. But here you need 5 minutes for each door. What will happen in between? What will happen in between? If you produce here if the cycle time here is 1 second and the cycle time here is 5 minutes, 300 slower. Here you will get inventory. So you will get work in progress. You call it work in progress. Work in progress. This is inventory, WIP. Important word. We will be talking about WIP all the fucking time in this lesson. We want to minimize WIP so that we get better performance. Zero WIP means zero output. So another very important concept. Please look, everybody here, all your senses. This is the Newton's law for logistics or for process management. Entschuldigung. Ich wollte in der Mitte treffen, aber es war Volltreffer. Entschuldigung. Yeah, it's okay. Ich habe mehr. Please look. Sorry. Please look ahead. Please look ahead. This is super important. Little's law. Okay, Little is an engineer that discovered this law that is true for any process. It's true for one machine, it's true for a factory, it's true for a whole corporation. Okay? And this law says that throughput so TH equals work in progress divided by output by lead time, sorry. Throughput is WIP divided by lead time. In German, Output oder Ausbringung ist gleich Umlaufbestand geteilt durch die Durchlaufzeit. Okay. Throughput is measured, of course, in parts per time. WIP is measured in parts, and lead time is measured in time. Ausbringung ist Stück pro Zeiteinheit. Umlaufbestand ist Stück. Durchlaufzeit ist Zeiteinheit. So, I write it again. Throughput equals WIP divided by lead time. This means this is equivalent to say that WIP is throughput times lead time. This is equivalent to say that lead time is WIP divided by throughput. Okay? These three things are equivalent. And a very good way to remember, please look at here, a very good way to remember is to always put the units, because you see here parts per time and here parts per time. So you see it's correct. Do not know it by heart, just try to understand, okay? When, okay, I let you copy. Your friend is not coming no more? No? Chicken out? So just one thing here. If throughput, if you want to increase throughput, if you want to increase the output of your process, you can increase your WIP or reduce your lead time. Because increasing WIP is not a good business, as we will see later on. Best strategy is to reduce the lead time. Why is increasing WIP not such a good strategy? Intuitively. Anybody? You have to keep it. You have to keep it. You have to storage it. So your holding cost, as we saw last week, goes up. So if you increase your WIP, you increase your holding cost. It's not going to be a good business. So if you want to reduce your WIP, you can either increase your output or reduce your lead time. But the bad news is that your output cannot be increased ad infinitum because your customer might not be wanting to buy it. So the best business is to, again, reduce your lead time. You're faster. Why is it good to reduce your lead time?
Now, more time is less, so you
The lead time is shorter.
shorter, you can produce more parts.
The important thing is that you can be faster. You can react faster to your customer.
The process is smaller.
The product cycle is shorter. Okay. So if you instead of having a lead time, just imagine you go to the car dealer and you say, I want to have the new Toyota Corolla. And you say how long it takes. They say 1 month, 1.5. And then you go to the next and you say, hey, I want to have the next the new Nissan. They say you can have it today. You might take the Nissan, even if you want first the Toyota, because the lead time is shorter. So shorter lead times lead to shorter product cycle times, to shorter product lead times, and lead to faster customer demand replenishment. So you deliver faster if your lead time is shorter. So if you want to reduce your lead time, either you reduce your WIP or you increase your throughput. So I repeat, the best strategy is try to reduce your lead time so that you have, and you do that by reducing your inventory in a controlled way. All three ways to explain Little's law are valid. All are the same. Okay? This is very important. So try to argue. I give you 5 minutes with your partner. Why? Your colleague. These lines go up and down, if it makes sense, and why. And we'll talk about it in a minute. Now solving question 1. What is the production plan? And for this, we need, of course, some data. Cycle time of machine 1 is 5 seconds. Oh, no. 5 minutes. 5 minutes. 1 day, 1400. No, less than 5. Otherwise, we don't get it. 3 minutes. And changeover time of 1 is, wait, no, 3 minutes won't make it either. 1800, no, it needs to be less than 2 minutes. And changeover time is going to be 5 minutes. So we produce every 2 minutes 1 part of A, 1 part of B, and 1 part of C. And to change from product A to product B, we need 5 minutes each time. Okay, that's the meaning of it. And then change cycle time 2 has a cycle time of 1 minute. A changeover time 2 of 5 minutes too. So we can see that machine 1 is slower than machine 2, right? Slower. Every 2 minutes I produce 1 part, and here I produce 1 part every minute. It's double as fast here as here. So we want to know the daily production plan of both machines. And to do that, I personally like to explain it for the first time like this. I think it's the easiest part, it's the easiest way to understand it. I take the first start of the shift at 6 in the morning, and then I say, well, I start with product A on machine 1. Product A. So it takes 2 minutes for each part, and I need to produce 300, right? So it's 600 minutes, 10 hours. Takes 2 minutes times 300 parts. Repeat this part. Machine 2 takes product A, 1 minute times 100 parts. 1 minute times 300 parts. Sorry. 300 minutes. Is this correct? Is this correct, huh?
5 hours.
It's correct. Okay. So 5 hours, 300 minutes. No, it's correct. Then changeover time from A to B, 105, 1105. Then 1 minute times 200, so 200 minutes. Then changeover time from B to C, 5 minutes more. Then 1 minute times 100, 100 minutes more, and then changeover time. So with this sequence, we produce every day the same parts. Every day we produce the same parts from A to, and A, B, and C in machine 1 and 2. But the question is, so this is question number 1. Okay, so we have question number 1 already. And the question is the next, how much inventory should we carry in between? We will focus on that in a minute. Any questions on this? Anybody? Does it make sense? Okay. So the second question is, how much inventory should we carry between machine 1 and machine 2? This means how much inventory of A, B, and C should we have between machine 1 and machine 2? And once we have understood this, we can answer this question easily, or somehow easily. So question number 2, in order to answer question number 2, we need to understand the nature of inventory, okay? And I want you to think about inventory as a huge water tank, okay? Imagine we have water in here, painted blue. Okay? This is the input of the water, the supplier, and this is the output. Okay? And this is the inventory you have, the level of inventory. What is our goal by defining how much inventory we have? But the level of this inventory is never 0. Because if we achieve level 0 inventory, then guess what happens with machine 2? It's dry. Cannot keep producing. If I don't have products here of product C, because machine 1 is not producing them on time, then this guy cannot produce product C to the customer. So I never want to be 0, but I also never want to be very high. So we want to calculate the minimum inventory. More is no problem. Only a matter of space. Only a matter of cash. Less than that means that at some point you will be out of stock. And out of stock means you lose customers. Okay? So if we think about inventory this way, then it will be a little bit easier to understand what happens here. Because every two minutes, I take one part out of machine one. And every minute, I take one part out of inventory between 1 and 2. This is a direct conclusion out of this fact. Every 2 minutes, I spit one part out of machine 1 because cycle time is 2 minutes. But every minute, double so fast, I take one part out of this inventory. So this means that in our case, the speed of input is how much? How many parts per minute go in here? One divided by 2. Every 2 minutes, I take one part into the inventory. So every minute, I take half of a part, right? What is the speed of output? One divided by 1. Every minute, I take one part out of this inventory because I take one part so that machine 2 is producing, right? So this way we can, with this concept, we can, if we knew the time that this input and output are open, then we could know the inventory level we need because we know the speed of water intake, we know the speed of water outtake. If we knew the time that both valves are open, we could know how much inventory we need in order to be able to regulate these differences in speed. So, and the time these valves are open can be easily calculated because it's the time between, this is Anfang or beginning of output. Remember, machine 2 is taking out, so I open the output at 6 in the morning and I finish the input end of input, of course, of product A at 1600 hours. In this time, both product A's are open. And I need to make sure that I have enough water in between so that I never get dry. Okay, so the formula is for inventory of product A is time begin of output minus time end of input times the differences in speed, the balance, speed of input minus speed of output minus a security factor. I usually put it 1 plus the security factor. Do not bother about the things, okay, about the signs. You can also put here the minus and here the plus. It doesn't matter. Okay. In the end, we just want the absolute value. So, time beginning of output until end of input, 600 minutes. Times speed of input minus speed of output, 1 minus 1 times 1 plus 1. I usually make alpha equal to 1. You can do that, and it's usually a good decision. So this means this is 600 parts. So the minimum inventory that we need for our part A is 600. Please try to do the same for part B and part C. Please pay attention. Begin the output of product B is here. End of input, product B is at 22:45. So if we do the same calculation is well, from 11:05 to 22:45, it's 11 hours and 40 minutes. So it's 660, 700 minutes. Times 1 second minus 1 times 1 plus 1 equals 700 parts. And delta C is the begin of output is here. The end of input is here. So we start at 14:30 and we end at 2:10. It's 12 hours later, minus 20 minutes. So 12, 6, 7, 20 minus 20. Again, 700 minutes times plus 1 plus 1 equals 700 parts. Okay, this will be solution to question number 2. Any questions? we answer how flexible or how we measure flexibility of a process, we need to answer one question more, and is if depending on the relationship between cycle times machine 2 or process 1, process 2, what do you think if cycle time of machine 1 is smaller than cycle time of machine 2, do we need inventory? Why? This one is faster, it's filling faster, so the only thing we need is first in, first out. Okay? Do you know what first in, first out means? Is it a funny joke to say first in, first out? No? Is it cool? Okay. So if cycle time 1 is smaller than cycle time 2, cycle time 1 is smaller than cycle time 2, means that machine 1 is faster. So it feels faster, which means that we never ran out of water in our tank. So it's full. Because here we have a huge intake, and here a super small output. So it's always full. Always full. The only thing we need is that the things that get in, get out in the same sequence. FIFO. First in, first out. We will explain later why, or I guess in 2 weeks. This is machine 1, this is machine 2. Now imagine you have cycle time 1 and cycle time 2, and cycle time 1, as was the case here, we had here 1, 2, and here we had 1 in our example before. Cycle time 1 is bigger than cycle time 2. No, good, no, but no. We always need FIFO. So what do we have? No, we have stock. We do need stock because this is slower. So we have the opposite here. We have a big outtake, a small intake. So it's going out more faster than we are taking in. So we need inventory, but a certain sort of inventory. Do you know what part? What sort of? So what we need here is something we call a supermarket. A supermarket. So just when you go to Rewe or to Kaufland or something like that, and then you buy your yogurt. Please pay attention in a second. And you buy your yogurt. You go to the cashier, and then it does beep beep. Okay. The signal is telling the system that you have taken some yogurt out of the shelf, and it needs to be replenished. Okay. So this is the shelf. This is you. This is you. This is the shelf, and this is the inventory. So you take some yogurt out. You give a signal. It's been taken out. Please go to the inventory or to the laga or something like that and replenish that. So you go there. You're out. You take your piece of yogurt to the cashier. It beeps. Okay, you've taken it out of the shelf, and then once you send the signal, you send a signal to the warehouse. Please deliver another yogurt because Monica just took one. Okay, this is called pool. We will talk about this in the next weeks. Or Kanban. Have you heard about this in the first semester? Production management and Beschaffungsmanagement. Have you heard about Kanban? Yes or no? Yes. Okay. So this is a pull process. This is a push process. Huh? Push and pull. Push means you produce without looking at the customer's demand. Pull means you produce looking at the customer's demand. Okay? Good. So what it takes us is that if you have a faster intake than outtake, then you don't need supermarket. If you have a slower intake than outtake, then you need a supermarket. And a supermarket is something easy to define, very difficult to implement. In a supermarket, you need a minimum, you need a maximum of inventory, and you need FIFO. So a supermarket is a sum of minimum plus maximum plus FIFO. Okay, you need 3 of them. This is per definition. Okay? Any questions? Okay, make another picture. Measure flexibility of a process with the KPI, key performance indicator. Every part, every interval. Short A E pi. Okay, you've heard of it before? No? E pi. This describes the minimum amount of time that it takes to produce the customer demand in that time period. Example, if we have one epi of 1 week, it means that it takes 1 week to produce the weekly demand. If we have one epi of 1 day, similarly, it takes 1 day to produce the daily demand. And so on. Okay? What is better, to have an epi of 1 week or to have an epi of 1 day?
1 day.
1 day. Why?
Because it's faster.
No, it's because every day, yeah.
If you produce it on 1 day, you have more in stock.
No, the other way around. So just imagine we have product A, changeover, product B, and product C. And this is one month. Okay? Imagine we have, this is 1 month. We have here one epi of 1 month. We can produce the monthly demand in 1 month. It's okay. But now imagine we can cut this in 4 weeks. 1, 2, 3, 4. And every week produce just a fourth of the demand of A, the weekly demand, which is 1/4. Then we do the changeover. Then we produce 1/4 of B. We do the changeover and we produce 1/4 of C. We do a changeover, and again we repeat this 4 times. 4 times. In the end, if we add up all these A 4 times, because this is 1/4, we have the same. But imagine that on day 15th, a thunderstorm comes and breaks my factory. And I cannot deliver for 1 week. So I lose. If I am in 1 epi of 1 week or 1 month, what happens? I have produced everything for A, a little bit of B, and nothing of C. So customer C gets fucked. But if we have an epi of 1 week, I have produced a little bit of A, a little bit of B, a little bit of C. So I can deliver to all of them. I am more flexible. You understand? If the epi is 1 day, questions? If the epi is 1 day, then I take 1 day demand of A, change over one day demand of B, 1 day demand of C, and so on and so forth. I repeat that every day. This is what we did before with our example, creating a daily production plan. So what we want is to understand what is the minimum epi that is needed, or that can be used in our process. Okay? Does it make sense? Hello? Yes? So, questions?